All right, guys, we are going to talk about the tangent curve a little bit today. Uh, I'm going to kind of show you two approaches. I'm going to show you the approach of using the unit circle to develop your ordered pairs for the tangent. Actually, I'm going to start off using these two curves, which are the sine and cosine, which are pulled from the unit circle anyways. So it's really the same idea, the same thing. Just you might think about it maybe a little bit differently or a different perspective. We're trying to graph a tangent off of these. Okay. So when I look at these two curves, or when you look at these two curves, let me change the color real quick so we can talk about it a little bit easier. So we got the blue one and the red one, right? And the blue one and the red one, respectively, are sine and cosine. Okay. So let's see here if we put the. All right. So the blue one is sine, and the red one is cosine. And if I look at, let's say, just an x value right now is 0, okay? The sine has a y value of 0, and the cosine has a y value of 1, correct? Okay. Well, if we divide those by the sine's y value divided by the cosine's y value, that equates to the tangent's y value at x equaling 0. Does that make sense, everybody? Okay. We know tangent sine divided by cosine, right? So up there on those two curves are respectively off the unit circle. They are either the x values off the unit circle or the y values off the unit circle, right? Okay. The blue one is the y values off the unit circle. The red one is the x values off the unit circle. Okay. Plotted against radians. Okay. If I take the y values out of the blue one and divide it by the y values out of the red one, okay, for the same x value, they should give me the tangent x or the tangent y value at that same x value. Okay, so that's what we're trying to do here. What I've done is just created kind of a slider here that puts this vertical line through there, and that vertical line is just going to show me or tell me that. Oh, I don't want that one. That point right there and that point right there, A and B, share the same x value, right? Okay. So for instance, if I was at, let's see if I can get to 0.5, close enough to 0.5. If I'm at pi over 2, okay, that's the x value here is pi over 2. The x value there is pi over 2, right? Okay. And if we go back to the unit circle, at pi over 2, right now what we're talking about is that ordered pair of 0, 1, right? Okay. Well, this is the y value. This is the x value. Okay. So here we'd be taking this value here, this A point's y value of 1, and dividing it by B's y value. It should actually be 0. This should be 0.5 pi, but I can't, just the way this is set up, I can't get that. That should be 0. I should have 1 divided by 0. Okay? And that's going to produce then the y value for tangent on the x value that is defined by this line going through A and B. Does that make sense to everybody? Okay? So I got to create a rule here that's going to help me find that x value. So what I'm going to do, and this is one of the nice things about GeoGebra that Desmos does not do. I can say I can write an ordered pair here. I can say let's just call it t for tangent. We'll say t is equal to, now the x coordinate I want to be the same as the x coordinate for A and B. Okay, and they are defined by, and right here they're 1.15, but they're being defined by this A up here, right? So I'm going to say A, comma, okay? Now I want the y value of my tangent point to be the quotient of A and B's y values, okay? So the way I can do that is I can say I want the y value of A, and we'll divide that by the y value of B, okay? So that is taking the If I think about the y value of A, that is the sine, and take the y value of B, that would be the cosine, right? Does that make sense, everybody? Okay, so this right here is saying sine divided by cosine. If I hit enter, it should plot a point that is on that same line A, okay? So it's collinear with A and B, okay? And it's equating to the quotient of those y values. Now, as I move A around, we see, obviously, because we're taking two different numerators and denominators, so I should have a different quotient, right? So what I'm going to do, just kind of move this over. Let's just move it over to about right there. And I'm going to ask GeoGebra to start tracing that point T, okay? And I'm actually going to, we all get the idea of what's going on here with the curves. I can take the curves out. Take those out just to eliminate a little bit of clutter. But A and B are still on those curves. The curves are just hidden. As I start moving A and trace T, I want you to see what that curve looks like. Okay, so that is what we end up calling one cycle of the tangent, or one period of the tangent curve, okay? And why is it one period? Because we start seeing it doing the same behavior there, right? And we start seeing it doing, oh, my slider ran out of room. All right, so, oh, that's terrible. That's putting too big of, the increment was putting too big of a gap between successive points, and you weren't seeing enough of them. All right, so let's get that down. All right, so we're there. And as I move this thing through, so going back this way, we see that thing is periodic, right? And it's going to go off in both directions as far as we want that thing to go, showing the exact same behavior, okay? Now, towards the tops and the bottoms of this curve, you start to see this gap getting larger and larger, right? The idea is that there should be, a y value that is bigger than this one, okay? An ordered pair that has a y value bigger than that one. And there should be a y value that's bigger than that one, and it keeps going up and up. The range of this thing is going to go from negative infinity to positive infinity, okay? But we have some issues here. What is it? If I put pi over 2 here as a line, x equals pi over 2. What does it look like this curve is doing towards that line? Especially if I'll just write the tangent function here. When you scroll, it disappears the trace, causes the trace to disappear. What do you notice about the blue line, which is the tangent, and that black line? Is there always a gap between them? So what do we call that black line? That's an asymptote, okay? Now, why is it an asymptote? When did we have asymptotes in college algebra? It was one of the main situations that asymptotes showed up. Division by 0, okay? On the unit circle, if I'm moving around the unit circle, I'm just going to look at these ordered pairs here. If I take the tangent, and we know that tangent of theta is equal to sine of theta divided by cosine of theta, which is the same thing. Sine of theta on the unit circle is your y value. Cosine is your x value, right? And these ordered pairs. If I start looking at the ordered pairs, they're going to be in the format of theta, comma, sine of theta divided by cosine of theta, how you want to write it, or y over x. Let's write it y over x right now. So let's start coming up with some ordered pairs that we know should exist on the unit circle, or not on the unit circle, the tangent function that come from the unit circle. And it's exactly what that last application was showing us, that last animation of tracing those points and highlighting those, okay? But I want you to do a little bit of the algebra here to see why those asymptotes show up. If I look at theta being 0, okay, which we've got either 0 or we'll do 2 pi at the same time, I have y divided by x, right? This is my sine, this is my cosine, okay? So going back to the last picture, I think they were even the right colors. This would have been your sine, the blue curve. This would have been your cosine, the red curve. If I take 0 divided by 1, what's 0 divided by 1? 0. So on my tangent curve, I'm going to have those 2 points, okay? But there's some other really nice points that we could have. You could have that one, okay? I can take 1/2 divided by radical 3 over 2. It gives me radical 3 over 3. Okay, but that's not a really nice number. I think it's like 0.577 or something like that. It's really not a nice number to plot. Okay, much like, there's an ordered pair there, isn't there? Okay, for that green dot. But those ordered pairs, those x and y values are even uglier, and their quotient is going to be even uglier. So we don't really want to plot those. Even though these x values and y values here are ugly, okay, can I still take, we're on this way, can I still take radical 2 divided by, or over 2, divided by radical 2 over 2? And what's that going to give me? 1. So that's pi over 4, and my quotient then would be 1. So at pi over 4, my tangent value is 1. That's why if you were to type on your calculator tangent pi over 4 or tangent 45, it spits back 1, right? Okay. Let's keep going around. Keep going around. We get to another convenient value there, which is pi over 2. And now what's that going to give me? 1 divided by 0, right? What does that mean? That's undefined. So at pi over 2, you get an undefined value. What that means to us, why we say the word undefined means it is not a definitive point, right? It's not defined. It does not exist, okay? So at pi over 2, there is no y value that exists. So graphically, we insert a asymptote, right? Okay. And what you guys would have recognized, what you could find out, that if, I don't know if I've got enough going on here that I can actually show the values here. Okay, so where is that? Where I got that coming from? All right, let me. I know it's messy, but let's see here. I'm going to show the ordered pair for that point right there, right? And now it's just got some rounding things here that are taking place. So that ordered pair right there, okay? What I'm going to do, because the tangent is the quotient of those two things, right? So I'm going to take the y value of x and divide it by the x value of x, and just see what that number gives me. And it should come up here, right there, 3.2749, okay? But as I start moving, okay, so you see here, it's 1, right? That's because it's taking radical 2 over 2 divided by radical 2 over 2. Now, liberty is there with rounding. But what happens to that number, as I get closer and closer to pi over 2, what is happening to that number? It's getting what? Bigger and bigger, isn't it? Okay. Now the logic is, well, this is kind of a calculus thing. As that point gets closer and closer, that number gets bigger and bigger, right? Now it's just because of the settings, it's snapping me to that point. And you see here that once it gets to that point, it's doing that. That's a very, very large number, right? Okay. So what we're saying here is that if I'm just to the right, and I can get that point back off, if I'm just to the right of that, so I don't have division by 0, okay? But if I'm just to the right, I have something divided. I have a number really close to 1 divided by a really, 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 really small number. What's a large number divided by a really, 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 really small number? It's a huge number, right? It's a number like 1,633,1,2,3,9,3,5, that number down there, right? Okay. So isn't that the idea of asymptotes? As we approach that asymptote, our y value is getting either really, really, really big in the positive y direction, or really, really, really big in the negative y direction. Okay. So just wanted to kind of show you that and maybe open your eyes to that as we're looking for these points, and it shows the behavior that we have at this asymptote. Okay. What if I go to this point over here of 3 pi over 4? What's that tangent value going to be? 3 pi over 4 tangent value. And the numbers are here, and you can divide these in that order. It'd be -1, right? Okay. What about if I go to pi? Now I'm dividing those in that order. That's the numerator, that's the denominator, right? Gives me 0, correct? Do we get the idea of what's going on here, guys? Okay. If I go to, I'll just go to 5 pi over 4, which is this spot right here. Okay. So it's going to be a radical 2 over 2 divided by radical 2 over 2, but they're both negative over here, aren't they? Well, it's going to give me a +1 as a quotient. What's going to happen at 3 pi over 2? -1 divided by 0, right? What's -1 divided by 0? Undefined again, okay? So you end up with another asymptote there, correct? Okay? So that's kind of what I want you guys to understand and realize when we graph the tangent function is that we're going to first, I think it's a good idea to first put in your asymptotes. So for us right now, the first asymptote is at pi over 2. Okay? There was another one at 3 pi over 2. If you want to put that one in, go ahead and do it. Okay? And this might show you a relationship that we're going to use here in a moment that tells us the distance between two asymptotes. What's the distance between those two asymptotes? It's pi, right? Okay. Well, the graph should be periodic. So I should be able to take 3 pi over 2 and add pi to that to get another asymptote, right? Does that make sense? I keep adding pi to that to get more and more asymptotes. So, yes, this is a great set of asymptotes to look at. But can I also subtract pi? So if I say I want x equals, so pi over 2 minus pi gives me that asymptote. Okay, we like that one. Okay, we like to look at this one here more, I guess these two. We prefer to look between those two than we do these two. It doesn't matter, though. Just plotting some points that we knew from the unit circle. 0, 0 was 1, right? Okay. Pi over 4. Okay, so pi, when my radians is pi over 4, the sine divided by cosine gave me a quotient of 1. Okay. And you can do, pi over 6 or 3, if we want to do pi over 3, that would have been, so the sine of pi over, what's the sine of pi over 3? Radical 3 over 2, so square root of 3 divided by 2. Okay. And then what is the cosine of pi over 3? 1/2, right? Divide this by 1/2. It's kind of ugly with all the parentheses we need here. But you see it gives that point right there, right? Okay. And we keep doing that. Now, C is not a point that you ever want to put, but you do see it, that's a radical 3 right there. Okay. So at pi over 3, comma, radical 3, you have a ordered pair. But we also have, going through what we did on the last screen, we also had, 3 pi over 4, and that gave me -1. We had pi, and it gave you 0. You had 5 pi over 4, and it gave you 1. You get those points. Okay, 3 pi over 2 was undefined. We then had 7 pi over 4. If we kept going, we'd have 7 pi over 4, negative 1. You would have had 2 pi, 0. Okay, and you start to see that these 3 points, these kind of 3 points, D, E, and F, are going to get repeated here and over here. So my next point, maybe in this interval over here, is going to be it's going to be 9 pi over 4, add pi over 4, and it's going to be a height of 1. And what happened? Oh, 9 pi over 4, height of 1. Okay. What is this point right here going to be? What would be the x value that is halfway in between 0 and negative pi over 2? Negative pi over 4. And what would the y value do you think would be here? Negative 1. I get that point. And where does that point come from? That point comes from still the unit circle, but instead of traveling counterclockwise, it's now traveling that way, right? Because now this orange angle here is negative pi over 4, or if we want to think about that arc right there, it's negative pi over 4 radians. But it still gets that terminal point, right? Is that okay with everybody? Okay. I'm going to graph the tangent function just between negative pi over 2 and pi over 2 for the moment. That, guys, that orange curve is what you're going to want to commit to memory, because that's going to be, you remember yesterday how we used sine and cosine? We used 5 points on the sine and cosine. They're like 0, 0, pi over 2, 1, pi, 0, and so forth for those two functions. So we could take a parent function and graph it, and then use that to transform and find the family of graphs for sine and cosine. Do the same thing for tangent. Okay? Those are the 3 points along with the asymptotes. So it's really 5 things that you want to commit to memory, so that you always have that parent function in front of you. And if you understand how that parent function works, you can then transform it and create any of the graphs from the family graph. Okay? As we look at this, though, guys, there's still symmetry occurring here. And just let me clean this up and get rid of. I think you can do it this way. Let's delete them. There's still symmetry occurring here. Notice if I look at my asymptotes, okay, is the y-axis right now splitting those asymptotes distance in half, or the gap between them, okay? Is this point J, does it have an x value? If I put x equals negative pi over 4, does J have an x value that splits the interval here between that asymptote and the y-axis? Does that make sense to everybody? If I put positive pi over 4 there, does B have an x value that splits that little interval in half? Does that make sense to everybody? We seeing that similarity that we saw with sine and cosine of the intervals getting split in half. So our tangent function, if I have that information there, we should be able to cut and paste it and get the rest of it. Okay. Now, when we graph it, it never puts the asymptotes in for us. We'll talk about here in a moment how we get those asymptotes. But that's your tangent function, and we can transform that. Does that make sense to everybody? Okay. Stop me if you're confused with something, doesn't make sense, want something explained again. But I'm going to look at this curve, and I'm going to make it kind of hard to see because I want to do a transformation. Okay, I want to do what tangent of maybe 2x looks like. Okay, something that we need to know for the tangent function, and I stated this, and it's simply the distance between two asymptotes. The period of the tangent function is different than the period of sine and cosine. The period of the tangent function, the distance on the x-axis takes to start repeating itself is what? Yeah, period I'm going to write this down for tangent of x is pi. Okay? That's going to change things in regards to our little formula that we use to determine the period of something that's transformed. That value is b, right? Okay? So that's going to provide then, that's b. It implies then that your period is 2, or sorry, not 2, it's pi over b. Is that all right with everyone? Okay? So our period in this case would be pi over 2. All right? How does that change these things? Those are the asymptotes for the parent function, right? And this distance from 0, 0 to that asymptote is half pi, correct? Or pi over 2. Okay? Well, if my period is only pi over 2, doesn't it make sense that I should have an asymptote at pi over 4 and an asymptote at it's kind of weird how I had that set up. Negative pi over 4. Does that make sense to everybody? Is that still kind of evenly spaced along the y-axis or against the y-axis? Okay. So now let's put some points in here. Okay. The parent function, if we looked at the parent function, it's kind of the ghosted image in the back here. Does it inside its one interval or its fundamental period have an x-intercept at 0, 0? So this function as well, tangent of 2x, is going to have an x-intercept at 0, 0. Okay. If we go all the way back to the tangent function, okay, halfway in between that little interval right there, you reach the height of 1. Okay. Now that interval is pi over 4. So it's halfway in between pi over 4. Pi over 8. So at pi over 8, you're going to have a y value of 1. And now what are you going to have here? At negative pi over 8, you have a y value of negative 1. And that then is enough for you to get your tangent of 2x. And right now it's only in the interval of negative pi over 4 less than x less than pi over 4. Okay? We've got that smooth curve, right? And you see then how that was a transformation of the parent function. Okay? We could then obviously cut and paste that, replicate that, and get the rest of it. Is that doable? Okay. What time do we get out here, you guys know? Say again? 34. Okay, we got one thing I got to talk about, or I want to talk about. And if we don't finish talking about this before the bell rings, I will finish it on the video. What they want to know, guys, a lot of times is what is an equation? What is an equation for your asymptotes? What is an equation for your asymptotes? And maybe tomorrow when we start off, I'll work through this again. What's your asymptotes equation? Okay, it's always going to be x equals. Okay, now we're going to go pi over 2 because that's the period of the parent function. Okay, but if there's a b value, we're going to put b down here because that in the last one the parent function's asymptote was a pi over 2, right? But our b value was 2, and you see if I multiply that by 2, it gets me the pi over 4 that I need there, right? Then I'm going to add essentially my period, okay? Which my period is pi over b. Okay? That is going to be the formula for finding one asymptote. We'll talk tomorrow how we can find all of them.
You forgot to change the quiz grade. You put it as a 97 when...
Okay, so this, we're talking about this formula. Okay, this b here, and you know, your normal, if we just look at the tangent function, tangent of x. Your asymptotes are going to be at pi over 2, plus then they're going to repeat every period, and the period for tangent is pi. Well, if this is 2 here, or 3, or 4, that fundamental period of pi over 2 for the tangent function is actually divided by whatever that number is. So it's cut in, if it's 2, it's actually pi over 2 is cut in half. If it's 3, it's cut in thirds. So there needs to be that b value. So when I write this as tangent of bx like that, our first asymptote is going to be found at pi over 2b. Okay, we're 2 b's in the denominator. But then how do I find the next asymptote? Is I add the period. Well, if this was a b, if this is a number other than 1, my period is going to be pi divided by b. So that is why we have this formula up here. Okay, it's because of the where the first period or where the first asymptote shows up, and then add to it the period to get the next asymptote. But if I do that, it's only going to give me one more asymptote. Okay, so for instance, I'm going to get rid of these and just start off from scratch. If I were to write, now remember this curve that I have here is tangent of 2x. So I'm going to write that I'm looking for the asymptote x equals, okay, I'm going to go pi over 2b, but b is 2, so 2 times 2. And you do see that gives me that asymptote, okay? So I'll just hit enter, and now I'm going to do the same thing. Let's see if I can do this. Alright, so that gives me the first asymptote right here. I want the next one, okay? So I need to add my period. My period was pi over 2. So I'm going to add, take that number, plus pi over 2, and you see that gives me that next asymptote. And then I would take that asymptote and add pi over 2. Well, that gets kind of to be a pain in the butt to do it that way. So what we do to come up with the infinite number of asymptotes here is that we come up with the formula that says x, your asymptote, is equal to, like I said, pi over 2b plus pi over b, okay? We'll put a k on the end of that. And that k is just for this part, okay? So this is the first asymptote. Pi over b is what we refer to a lot of times as like a counting tool, or maybe an index that allows us to get the next asymptote. What is this k? The k is what k is really the index. K is a number that belongs to the integers. And remember, your integers are these. They're -3, -2, -1, 0, 1, 2, 3, and they go off to positive and negative infinity. There's no fractions or anything in there. So that makes this thing here always a multiple of pi over b. Okay, and if I write this, let's see if I can do this right. We got pi divided by 2 times 2. Okay, because our b in this case for this tangent function was 2. And then I'm going to add to that pi over b, which b again was 2, times then k. Alright, and so it asked me to create a slider for k. What's going on here? I've got k as something else here. So let me just delete this, see if that. Delete that, and okay. Right. So create a slider for k. I'm going to allow that to be, that's fine, just find the first few. So what this is doing is this is allowing k to go from -5 to +5 by increments of 1. So that talks about my integers between -5 and +5. And let's just make that so this number here, that was the the location, that was the equation to provide the x location of my asymptote. This is my counting tool. Now I need to have something that actually shows the asymptote. So I'll write x equals a. And a is this number here. Okay, so we got x equals 3 pi over 4. And what we can do, I'm gonna put in the entire tangent 2x function here. Clean things up a little bit. And now as I move k, you can start to see the repetitive asymptotes kind of show up here. Maybe, if we can get this thing to stop. Alright, so if I go change k, you see our red asymptote mimicking the spots where the asymptotes should be. Okay, so that is a nice formula to have as we're working the next couple sections. Let me take this real quick. Let me say that this is I'll make this a b value, so b times x. That's going to ask me to create a slider, so create slider. And then down here, I'm going to make this, so that would have been b, and this would have been b. Alright, so now I'm just going to change, so this changes the overall function for the tangent. Let me get rid of that tangent 2x. Alright, so this changes the period, but you see now that as that period changes, the way we've got that written in, that formula, the asymptotes will change accordingly as well. Okay, so something to commit to memory. Maybe it'll take you a couple times to kind of look at that video and watch that and understand that. But what I want you guys to know is, I just want to get rid of everything, I guess. Your asymptotes are found at pi over 2b plus pi over b times k, where k is an element of your integers. And again, your integers, remember, and it's like, for our groups of numbers, they use kind of capital, cursive, fancy letters. That's a z. They go from negative infinity up to your negative 2, negative 1, 0, 1, 2, all the way to positive infinity. Okay. Hopefully that helps, makes a little bit of sense to you. We'll talk about some of this stuff a little bit more tomorrow or the next day.